here's where we are. We are doing preparatory work to getting to the important and last section of our work on non-monotonic logics, which is the history of confirmation theory and some of its details. In order to get there, the first thing we did was talk about the probability calculus and then talk about ways to link that with the rationality of opinion, which will turn out to be central for how we turn to applying this material in confirmation theory. When we talked about linking principles of logic with the rationality of belief, we began with the notion of comparative entailment. Comparative entailment seems to support many of the axioms of the probability calculus. In fact, it looks like it generates a good argument for all of them, except for the finite additivity requirement. So comparative entailment says you should be at least as confident of the entailed proposition as you are of the entailing proposition. So if P entails Q, your confidence level for Q should not be lower than your confidence level for P. After all, that's what entailment guarantees about truth. Okay, so suppose you endorse all of that and then you see the equally decent argument for finite additivity. You are now a probabilist. You think in order to have rational credences, you have to conform to the probability calculus. Now, in addition to that synchronic requirement, there are various diachronic proposals that can be given, building off of the first one, which is conditionalization. It tells you when you learn some new information, E, set your new attitude toward any proposition A to the same value that your earlier conditional attitude toward A was conditional on the evidence that you just acquired. So your new attitude toward A is the same as your old attitude toward A conditional on what you learned. That's conditionalization. Other principles that we looked at to supplement probabilism plus conditionalization look like they presuppose something like conditionalization. These are the deference principles. You might want to defer to chance, or you might want to defer to experts, or you might want to defer to your future self or selves. In all such cases, it looks like what's motivating the view is that if you knew what the experts think, then you ought to change your opinion to agree with them. And if you knew what the objective chances were, you would want to change your opinion about A to conform to what the chance of A really is. And maybe as well, if you knew what your future, smarter, better informed self will think about a subject matter, if you trust yourself, you should set your current opinion to match the opinion that your future self would have. Now, all of that is put in the language of what your unconditional attitude towards something should be once you learn something about what you should be deferring to: objective chance, expert opinion, future self attitudes, that sort of thing. All of the principles are put in terms of conditional probabilities. So a good way to see what the conditional attitude requirement is doing is it's putting in conditional form the information that you would use by conditionalization to update once you learn that the condition held. So your conditional attitude toward A, given that the objective chance for A is X, should be X. And then if you update by conditionalization after learning what the objective chance is, your new attitude will match what the objective chance is. That's just how conditionalization works. It takes your current conditional attitudes and then lets them govern when you learn that the condition is actually true. So that works for all of the deference principles. The additional principle that it doesn't help with is the regularity principle. The regularity principle says that you should never assign a contingent claim an extreme probability of either 0 or 1. As we noted, the regularity principle doesn't play very nicely with conditionalization, because conditionalization models change of opinion on the idea that you raise your probability in what you learn always to 1. You become certain of everything that you learned. That's what it is to learn something. But regularity tells you you should never be assigning a probability of 1 to anything unless it's a necessary truth. So conditionalization hardly ever applies, because the only thing that you could learn that would fit the model that conditionalization is imposing on you, the only thing that you could learn would be logical or mathematical truths. Okay, so regularity seems to undermine conditionalization as the right principle for how you update. What should you do in place of conditionalization if you want to supplement probabilism with some sort of diachronic requirement on rationality? Well, that's what Jeffrey Conditionalization is all about. Jeffrey Conditionalization, he called it probability kinematics in 1963 when he first published this material. But it's come to be called Jeffrey Conditionalization because probability kinematics did not convey any special information. So let's name it after Jeffrey. Jeffrey Conditionalization arises from an attraction to the regularity principle. Regularity doesn't play nicely with conditionalization, so we use Jeffrey conditionalization in place of ordinary conditionalization when we're in a situation where experience doesn't speak with the voice of an angel. Now, what that phrase means, that's von Frossen speaking, and the idea is this: sometimes experience is crystal clear and there's no question what you're supposed to learn from it. In other cases, things are murkier. So suppose you're at dusk and you're peering off into the distance and it kind of looks like your best friend stealing a television from an appliance, an audio-video store. Okay, what should you believe on the basis of this experience? The experience is a bit ambiguous. It looks like your friend, but you're not certain it's your friend. So whatever you're learning from experience here is not something that you can attach certainty to. So the idea is simple. Figure out what the possibilities are, and then you'll update based on how likely your estimate is for each of those possibilities. Let's look at the formula, and I'll draw you a picture to make sure that we know what we're talking about. Okay, let me bring up my little tool here. We have a logical space. We're trying to figure out how big this logical space ought to be. So this is how we're thinking about A. What attitude should we have toward this entire space? Now you have a current attitude, but you're going to update that current attitude. So the way you're supposed to think about it is you're going to partition this space into a number of subregions. Each subregion will be distinct from every other one. So they will be exclusive of each other. And to be a partition, the components have to be exhaustive of the space. So you could draw it into 2 spaces, and this space would be much bigger than that. Your partition could carve it into 3 spaces. It could carve it into, what do we have now? 1, 2, 3, 4, 5, 6 spaces. It makes no difference how the partition works in carving up the space in question. What matters is that the partition has elements that are exhaustive of the space. Every part of the space is included, and there isn't any overlap between the subregions of the space. So the partition is exhaustive and exclusive of each other. And in your opinion, no part of the partition is empty. So if you had a partition where one part was empty, just decrease the partition by 1, and you'll have a new space where all of the parts of the partition have a positive probability. So that's what you start with. After you do this partition, you learn the Jeffrey rule. The Jeffrey rule says we're going to calculate your new probability. J is a time later than I. So your new credence at time J, an unconditional credence in A, should be a function of two things. Your attitude toward each of the parts of the partition times a conditional attitude toward A on each of those parts. So you're looking at this way of partitioning. This one has what? 1, 2, 3, 4. 1, 2, 3, 4, 5. I think I counted 6 before. I did count wrong here. 1, 2, 3, 4, 5, 6. I guess it depends on if you see this line as connecting here or not. If it doesn't connect, then this whole thing all the way down to here is one region. But I don't care how you interpret this diagram. We'll just label the parts. So here's part B1. And we know what we're looking for is how big is the A part of B1? Given B1, how much of that is going to be A and how much of it isn't, right? So forget this part of the label. And then you have B2. You have partitioned all of logical space and you're asking the question for each of the components, how much of that component is occupied by A? So the logical space that we're thinking about is the space that covers both A and not A. And all we know is that each of the components has a non-zero value. So this is B4, and you want to know how much of the B4 space counts as A. And then, lastly, let's assume this little triangular part is part of B1 since I didn't actually connect the lines. How much of B5 counts as an A part of B5? Okay, so you do all of the conditional probabilities, and then you multiply them times the size of each of the elementary parts of your partition. How much of the total space does B1 take up? Well, bigger than anything else on this diagram. How much does B5 take up? You're going to multiply that times the conditional probability in question. And recall that this fits our way of expanding every proposition using its disjunctive normal form. So if you do the partition of B1 through B5, then you know A is equivalent to A and B1, or A and B2, or A and B3, or all the way up to A and B5. All right, so if you know that those are equivalent, the probability of A is going to have to be the same as the sum of all of these exclusive disjuncts, which are each conjuncts. And recall that A and B1 is the probability of B1 times the probability of A given B1. So in a way, everything on the right side, come back over here to the formula, the stuff on the right side is just giving you that big sum for this big long disjunction. So call this the disjunctive normal form expansion of A relative to this partition. That's a standard move that we will use over and over again in proving things and calculating things in probability theory. And Jeffrey conditionalization plays off of that. It takes a conditional probability, multiplies it by the size of the element of the partition, and then turns to the next element of the partition, figures out its size and multiplies it times the conditional probability. It's just using the disjunctive normal form expansion of A and the definition of how to calculate the probability of a conjunction, the general conjunction rule, to generate a value. Now there's one complication to that, and that's that the subscripts here are different. So the conditional attitude that you're using is the earlier conditional attitude, and the unconditional attitude is the later one. So we take your earlier conditional attitude times your later attitude about the size of B1 relative to the entire logical space, and we keep doing that for each of the members of the partition until we run out and exhaust the logical space in question. And that will be our new conditional attitude. So let's take a simple example. Let me clear the screen of all drawings. Suppose you're testifying in court about the event we spoke of earlier, where some audio video store was robbed, and you were looking and seeing what was happening, and you're now testifying that it was your best friend that you saw going away from the store. So then the defense attorney gets up and he says, how far away were you? What were the lighting conditions like? And you're honest, you say, well, I was 150 yards away and it was at dusk, so not ideal circumstances. And so he then gives you evidence which convinces you that the reliability rates for people like you in such circumstances is not great. Let's say the not B region takes up 75%. And the not B region is where you're not making a mistake in who you're identifying. In the B region, the other 25% is one where you are making a mistake. Now this will simplify our conditional probabilities quite a bit, right? Because the probability that your friend is the one stealing the television, given that you're making a mistake in who you're identifying, that conditional probability is going to be 0. And so you'll multiply 0 times, oh wait, B is the case where you are making a mistake, not B is the part where you're not making a mistake. So the probability that he's the one taking it, given that you are making a mistake, is going to be 0. And 0 times anything is still going to be 0. So we get 0 over here. Now, what's the probability that it was him taking the television, given that you're not making a mistake? B2 is not B on our diagram. Well, that's going to be 1, and we'll multiply that times 0.75. And so our new conditional attitude should be 0 plus 0.75, which is 0.75. Now that means the defense attorney did a good job of undermining you, because if your new attitude is 0.75 and he asks you, so how likely is it that you think it was your friend who did it? And you then report, well, I'm 75% sure that it was him. That's way below any reasonable account of what beyond reasonable doubt would count as. So the defense attorney succeeded. But that's how Jeffrey conditionalization works. Now, there will be homework problems where we talk about Jeffrey conditionalization when we get to the Teitelbaum book.